Hi dear friends, good morning to all. This is Bhavsar Sonone, Assistant Professor, Department of Chemistry, Gokhale Education Society's Arts, Commerce and Science College, Jawar, District Palakkad. Dear friends, in the previous part of this lecture series, we tried to discuss the Arrhenius theory, which is one of the important theory to explain the rate of reaction for complex reactions. We also tried to explain the different rate equation for various types of complex reaction, and in the last part of the video we discussed some numerical based upon the Arrhenius equation. Definitely we tried to solve some problems based upon the Arrhenius equation in integrated form at two different temperatures having rate constants K1 and K2, and we also tried to solve some another problems based upon the exponential form of Arrhenius equation. So dear friends, I think you have gone through all the numericals of the same type and there will not be any problem in the problems based upon the Arrhenius equation. Dear friends, today in this part of the video we are going to discuss again rate of reaction, but in this part we are interested to explain or to discuss the rate of reaction based upon the particular theory called as collision theory. Dear friends, just like the Arrhenius theory, because Arrhenius theory was useful to explain the rate of reaction, particularly to explain the temperature dependent rate of reaction, how the rate of reaction depends upon the temperature, or what is the relationship between temperature and the rate of reaction, that was explained by means of an Arrhenius theory. At the same time, this is another theory called as collision theory, and this theory is useful to explain the rate of reaction. Definitely the title of this theory itself indicates that here we are going to discuss about the collision between the molecule, and whenever we are seeing the collision, definitely the collision takes place in a gaseous molecule or between the gas molecules. So here definitely we are going to discuss about the rate of reactions involving gas molecules, in which how the rate of reaction depends upon the collision between the two or more than two gas molecules. This is the part of today's discussion. Dear friends, there are some assumptions based upon which the collision theory is able to explain the rate of reaction. First thing is that whenever we are going to talk about the gas molecule, definitely in earlier parts you might be well known that the actual behavior of gas molecule is well explained by means of a theory called as kinetic theory of gas. So whenever we want to explain all the nature or the behavior of gaseous molecule, then the kinetic theory of gas is useful to explain the nature as well as behavior of gas molecule. That's why in this part we are also going to discuss, or we are also going to use the kinetic theory for the gas molecule. But before this we will discuss some numericals, we will discuss some assumptions based upon which the collision theory is able to explain the rate of reaction. The first assumption is that according to collision theory, molecules, particularly gas molecules, are treated as the rigid sphere. The gas molecule is treated as the rigid sphere which describe only a motion called as translational motion. So here the first assumption is that according to collision theory, the molecules are treated as the rigid sphere. Rigid spheres means these are having a constant shape or the constant size, and this shows a particular motion called as translational motion. So this is the first assumption. So here in the first assumption, molecules are treated as a rigid sphere which shows translational motion. Again, according to this theory, these rigid sphere molecules are able to collide with one another for the reaction between them. means whenever the two reactor molecule will collide with one another, then the reaction between them take place. Means reactor molecule must collide for the reaction to take place or for the reaction between them. It means that unless and until the reactor molecule does not collide, the gaseous reactor molecule does not collide with one another, the reaction will not take place. So for the reaction, the reactor gaseous molecule must collide with one another. The another assumption according to this collision theory is that during collision what happens whenever the two or more than two gas molecules are colliding with one another, then the collision between them take place. But during collision there is only exchange of energy. So here during the collision exchange of energy can take place, means there may be energy transfer from molecule 1 to molecule 2 or maybe from molecule 2 to molecule 1. So this is very important. So during the collision there is only exchange of energy. So here the transfer of energy from one molecule to other or other to next can take place, but and no net gain or the loss of energy of molecule, but the no net gain or the loss of energy of molecules will not be there, and that's why means the total energy of the molecules remains constant. There is exchange of energy between the molecule, but the total energy of the molecule always remains constant. So this is the meaning of this assumption, that during the collision the exchange of energy is possible between the molecules, but the total energy of the molecules before and after collision remains constant, and that's why such collisions are called as elastic collision. Means if the energy of the molecule before and after collision remains same, then the total energy of the molecule as before and after collision remains same, then such type of the collision between the molecule is called as elastic collision. I hope you can understand about this. So you have to keep in mind in simple way. You can say that during the collision, the transfer of energy takes place within the molecule or between the molecules, but the total energy before and after collision remains constant or remains same. Such type of the collisions are called as the elastic collision. Actually, this is one of the important assumption which was also stated by kinetic theory of gas also. Next assumption, according to the collision theory, in order to explain the rate of reaction of the gaseous reaction, is that the number of collision between the molecule, what is the number of collision, because this number of collision is very important in order to decide the rate of reaction, because the rate of reaction depends upon the number of collision, that we will discuss in the next part or in the next slides. But this number of collision between the molecule which are treated as rigid can be calculated with the help of theory or with the help of assumption, actually with the help of or by means of kinetic theory of gases, because already I told you this is a theory which can explain all type of behavior, nature and all things regarding with the gas molecule. So the behavior of gas molecule, nature of gas molecule is explained by means of a theory called as the kinetic theory, and that's why whenever we want to calculate the actual number of collision between the molecules which are treated as the rigid sphere, we have to use the kinetic theory of gas. So here kinetic theory is used to calculate or to determine the actual number of collision between the gas molecules. Next, if we will discuss here, the next assumption is that during collision some molecule may gain energy or some molecule may lose energy. In short, you can say that there is exchange of energy from one molecule to other or other to one. So that is, this is simple way that during collision the transfer of energy takes place, but the total energy remains constant. Already we discussed in the previous one, and that's why such type of the collisions are called elastic collision. So during collision what happens, some molecules may gain energy, at the same time some molecules lose the energy, and that's why the total energy remains constant. And definitely all molecules are not able to show the reaction, or all molecules are not able to contribute into the rate of reaction, and only those molecules which has energy or which possesses the energy above certain value, above certain minimum value, sometimes above certain this minimum value can be called as the energy of activation, but only those molecules which possesses above certain minimum value will react on collision. Definitely this minimum value is concerned with the energy of activation. It means that only those molecules which possesses energy equal or above the energy of activation, only that molecules can be can react upon collision. So after collision, definitely the energy of the molecule increases, but that energy must be above certain limited value or the minimum value, and then these molecules can react on collision, and such collisions are called as effective collision. It means that only those collisions which are responsible for the reaction are called as the effective collision. It means that definitely number of collisions take place, but some collisions may have smaller energy. Definitely that will not responsible for the reaction, and only those collisions whose energy is having certain minimum value upon the collision, that collision will be responsible for the rate of reaction, and that's why such collisions are called as the effective collisions. And for the effective collision, definitely the orientation alignment of molecule is very important, and for effective collision or to have the effective collision, the molecule must be suitably oriented. Their orientation must be proper. Their orientation must be proper. Then and then the collision between them will be effective. It means that the collision will have the minimum value of energy upon on collision, and that is responsible for the rate of reaction. So it will be called as effective collision. It means that for effective collision or for collision to have effective, the molecule must have suitable orientation. Again, when the molecules take part in effective collision, at that time what happens actually, there is a conversion of reactant into product. So whenever the molecule take part in the effective collision, means effective collisions are only those collisions which are responsible for the reaction. Means on effective collision or in the effective collision, reactor molecule get converted into product. And during this, what happens? Whenever the reactor molecule get converted into product, definitely that take place through the formation of transition state. But whenever reactor molecules converting into product, at that time there is a rearrangement of bonds in the reactant take place that leads to the formation of products. Definitely we know the pathway of reaction. Initially the bonds in the reactor molecule broken down, it will be converted into transition state of the activated complex, and then it decomposes to the newly formed molecule that we called it as the product molecule. And here, according to the collision theory, when molecule take part in effective collision, the rearrangement of bond take place in the reactor molecule results into the formation of new molecule called as the product. So these are the most important assumptions. Next assumption given by the collision theory, the actual rate of reaction is very important, because we people are interested to define the rate of reaction. The actual rate of reaction is always directly proportional to the number of collision. Already I told you, actually it should be effective collision, but definite number of collision is very important, and the rate of reaction is always directly proportional to the number of collision per unit volume per unit time. It means that frequency of collision is very important. What is the number of collision take place in 1 minute or the 1 second, that is called as frequency. But here the rate of reaction is always directly proportional to the number of collisions per unit volume per unit time. This is very important. So here number of collision is directly proportional to the rate of reaction. Again, the number of collisions, whenever you want to calculate the number of collision, then the number of collisions is deciding the rate of reaction, and that's why the number of collisions per second per cubic centimeter in any gas is given by means of a theory called as kinetic theory, and the number of collisions per second per cubic centimeter by kinetic theory of gas is always given by z is equal to 2 n square sigma square under root of, this is under root of pi rt upon em. Definitely we should know the meaning of all this. Here this n is the number of molecules per cubic centimeter taking part in the collision during the reaction, and sigma is the collision diameter of the gaseous molecule which are colliding with one another. R is the gas constant 8.314. T is the absolute temperature at which the collision between the gas molecule take place, and M, capital M, is the molecular weight of the gas whose collision is going to take place. Again, the number of collisions, number of molecules colliding. Definitely for one collision we are requiring the two molecules, because it is not possible to have the collision within the same molecule. So for the collision we are requiring the two molecules, and that's why number of molecule colliding per second per cubic centimeter will be always double of the collision. It means that for one collision we will require two molecules, for two collision we will require four molecules, and that's why the number of molecules colliding per second per cubic centimeter will be always, or will be twice of Z for biomolecular reaction. What is to indicate biomolecular reaction? Means reaction involving two molecules. And for here regarding with the same, suppose we have the mixture of gas in which we have taken the two gas or two types of the gas 1 and gas 2, and number of collision between the gas molecule in the mixture of gas containing gas 1 and gas 2. So here in this mixture of gas 1 and 2, number of collisions take place per second per cubic centimeter is given by this equation, because earlier was only for the single gas, and here this is for the number of collisions for the gas containing the two mixture of two gas. So here this Z12 is equal to N1 N2 sigma 1 to square under root of, this is very important, it is again under root of, this is under root of 8 pi RT into M1 plus M2 divided by M1 into M2. Here N1, let me do this. Okay, here N1 and N2, these are the number of molecules of gas 1 and 2 respectively which are taking part in the collision. Sigma 1 2, this is the average molecular diameter. As the two molecules are different, definitely their diameter will be also different, and the sigma 1 2, this is the average diameter of both the molecules, and that's why sigma 1 2 can be calculated from sigma 1 plus sigma 2 divided by 2. M1 and M2, these are the molecular weights of gas 1 and gas 2 respectively. So this is the equation which can be used to calculate the number of collision between the two gases, or between the gases contain the mixture of two gases 1 and 2, and definitely we will be able to calculate the number of collision, and later this number of collision is deciding the rate of reaction. So dear friends, I think we have understood this very well, different assumptions of collision theory and how these assumptions can be used to calculate the actual rate of reaction, and how these effective collisions will decide the rate of reaction, that we will discuss in the next part of the video. Thank you very much.